Есть, да? Звук? Есть ли звук? Okay, so our last lecture was 3 weeks ago, and we finished with the following definition. So let me repeat the definition. We considered an ideal inside a polynomial ring on n variables. And then we said that a point or point, say with components alpha 1 up to alpha n. Well, you can think about this as a point in the n-dimensional affine space over the algebraic closure of this field, so field K. So this point is called an algebraic zero of the ideal I if you take any element f in the ideal, compute this polynomial on this point. Right, you can do this. Well, it's just a polynomial with coefficients in k. When you plug in these elements of the k bar, you get some element in the k bar. So it makes sense to say that this is 0. So if you wish, this is 0 in the k bar. And this is supposed to be true for any element in this ideal. And we prove the following theorem. So if I in the polynomial ring is an ideal without algebraic zeros, then in fact this ideal is equal to the ring, and for shortness I'm just writing generate by the one unit ideal. So I'm not going to prove this again. So today we're going to derive an important kind of corollary, but I'm going to call this again a theorem, one of the famous theorems of commutative algebra, that is the Hilbert-Nullstellensatz. So Hilbert's So which Nullstellensatz, which just means the theorem about zeros. So again, we take an ideal in the polynomial ring. And also suppose that we have an element f, which is just a polynomial. So if f is vanishing on any algebraic zero of the given ideal, then there is an m, some positive integer, such that f to the m belongs to this ideal. And if you know the previous theorem, the proof of this theorem is relatively elementary. So the main idea is to consider a new ideal. So let's define ideal J, which will be by definition a sum of two ideals. So this is ideal I plus principal ideal 1 minus yf. Well, what's variable y? That's just a new variable, so we consider this as an ideal in the polynomial ring, where we have all the variables as before, plus we have additional variable y. Notice that I'm using notation a little bit. So this I is living in this ring, So here I just consider kind of the extension of this ideal I to this new ring. So there is a slight abuse of notation, but to keep formula simple and clear, I just want to use it. Okay.
What's with vanishing on any algebraic zero?
Well, you consider ideal, right? You define a bunch of points in the affine space. So you can just take this point and compute on this point this given polynomial f.
Yeah.
If vanishing means that this is 0.
So f
On any algebraic zero, if you take algebraic zero,
so any algebraic zero of I is algebraic zero of f.
yeah, any algebraic zero of the ideal is also a zero of this polynomial.
Okay.
Okay. What you can tell me about the algebraic zeros of this ideal J?
All algebraic zeros of I.
Yeah, so at least we have all the, if let's fix some notation. So if we have some generators, so how many generators I want to use? Oh, maybe, I don't know, maybe m generators for the ideal I. So clearly in this sum of the ideals we have still all these generators. So, and if you consider algebraic zeros, so any of such generators has to be a 0. So at least if you're supposed to have algebraic zero, these things has to vanish on this algebraic zero. But if this happens, f is also vanishing on this algebraic zero. This means that the second summand is also, so in the second summand, this will be just 1 on this algebraic zero. So there are no algebraic zeros. So that's a new ideal, and this new ideal has no algebraic zeros.
When there's no algebraic zeros, probably it's some algebraic zeros.
No, so suppose you have an algebraic zero.
Yeah.
So then at least you have these elements. So this thing still belongs to the J.
Oh.
So then this is at least an algebraic zero of the ideal we started with, the ideal I. And if this is an algebraic zero of ideal I, looking at the second summand, we see that the second summand is automatically 1. So this can be 0 for all elements in the J. Okay, now we have this previous theorem that we proved in the end of the last lecture. We can say that J is in fact unit ideal in this little bit larger ring with one more additional variable. Well, now let's just write a polynomial identity. So I can say that there are some other polynomials, let's call them Pi, such that if you multiply on hi, take summation between 1 and m, and then there's one more additional polynomial q, 1 times 1 minus yf, this is 1, right? This is because this ideal is just a unit ideal, and I decompose 1 using all the generators of the ideal J. So the generators are h as before, and there's one more additional generator. Okay, so we get this polynomial identity, and now I just want to take this polynomial identity and replace y with 1 over f. Right? I can evaluate this polynomial identity when this variable is equal to 1 over this polynomial. So what I will get here, then the second summand clearly will be 0. So what's left is the following. I'll get, now I want to write arguments. So pi x1 up to xn. So that's the coefficient. No, there's also variable y. That's a coefficient. So pi is an element in this ring. So it also potentially depends on the variable y. So instead of y, I need to write 1 over f.
How do we replace it? What we do? Replace y with 1 over f.
I mean, just in the most naive way, as you do in the high school. Instead of variable y, you write 1 over f in the polynomial identity. So that's just this is polynomial which is equal to 1. In the polynomial, I can do this. I won't get the polynomial, of course. I will get just a rational function. But this is valid manipulation. So that's a coefficient. And then in the hi, I don't have any y's. So the arguments will be just x's. And this is equal to 1. The summation is still between 1 and m. So again, this is in the k, x1, xn. Notice that I'm using different parentheses to indicate this is rational functions, not polynomials. Okay, so On the right-hand side, we have 1. In the left-hand side, we have a finite sum of fractions. And the denominators of these fractions, what we have? We have only some powers of f. So clearly, there is some sufficiently large power of f such that if I multiply by this sufficiently large power, I just clear the denominators and get a polynomial on the left. So there is some positive integer m such that if I multiply by this sufficiently large power, well, potentially I'll get a different coefficient, so let me write this as gi x1 xn, still 1 over f, hi x1 xn, and this is equal to the fm, and this is not in the field of fractions for the polynomial ring, but in the polynomial ring itself. Okay, so there are some denominators. I choose sufficiently large power to kill all the denominators, and then I'll get the identity between polynomials. On the left-hand side and the right-hand side, there are polynomials. End of the proof. Right? Because Fm is presented in terms of the generators of the original ideal with some coefficients, which are polynomials. Okay. Let's derive a corollary from this, which is also sometimes called Hilbert-Naustalen Satz, but in the weak form. So let me say weak Hilbert, well, Naustalen Satz. Now, in this statement, I want to assume that K is algebraically closed. Notice that in the general version, we never used that the field is algebraically closed. So then any maximal ideal M in the polynomial ring is of the form, well, is of the form M is equal to the x minus a1, so x1 minus x1 minus a1, x2 minus a2, xn minus an, where all these ai's are in the K. So that's a statement that we definitely know for polynomials in one variable. We've done such examples, say, over complex numbers, and we saw that over real numbers there are other examples of maximal ideals which are not of this form. Okay. Proof. So ideal M that we consider, that's a maximal ideal, and of course I want to assume that this is a proper ideal, so it's not a unit ideal. So if this is not a unit ideal, so by this theorem there are no algebraic zeros again. So ideal M has at least one algebraic zero. So let's call this 0, a1, up to a. So that's exactly these numbers that we're going to get in the result. Okay. So if I take a polynomial f in this maximal ideal, well, then by the definition of the algebraic zero, I can say that if I evaluate on these a's, this polynomial f, I'll get 0. Well, now if I have this, I want to apply the Hilbert-Naustalen Satz to this polynomial. This is my f, but the ideal that I want to consider is this ideal. So applying Hilbert Nullstellensatz answers to the pair f and the ideal x1 minus a1 xn minus an. So well, clearly for this, clearly this is a maximal ideal corresponding to a point, and for this maximal ideal, we know all the algebraic zeros. That's precisely this one algebraic zero. So we see that the conditions of the Hilbert-Nullstellensatz ansatz for this polynomial and this ideal are satisfied. So for the ideal, there is only one algebraic zero.
Is there only one algebraic zero?
No, just look at the ideal. So this is the generators. So this is where all the generators are supposed to vanish. So if they all vanish at some point, this x1 is equal to a1, etc. So what we can say that there is positive integer m such that f to the m belongs to this simple maximal ideal given in terms of the generators, right? So maybe applying Hilbert-Nullstellensatz to this pair, we get this. Okay, but this is true for any f in the maximal ideal. So for any f, there is a corresponding power such that f to this power belongs to this ideal. Well, let's just rewrite this. So hence we can say that m is a subideal in the radical of the x1 of this ideal, this generated by the xi minus ai. Right? This is the same statement, but I'm just saying that this is, if this is true for any f, right? That's exactly this. So I take any element and some power belongs to this ideal, so it means that f belongs to the radical. So hence we have this inclusion. Well, can we explicitly compute this radical?
Well, this radical of maximal ideal, then it's just a maximal ideal.
Yeah. So this is just a maximal ideal. So the radical in this case doesn't do anything. So we see that this maximal ideal that we started with is a subideal kind of in this canonical maximal ideal with a very simple description. But by the maximality of m, it has to coincide.
So we just wrote that any maximal ideal has algebraic zero of 1 point.
Yeah, so there is a bijection between the maximal ideals of this ring and the point in the affine space. Of course, this is only over algebraically closed field. You already know that over real numbers, for example, this is not true. So if you wish, you can think about this as kind of application of ideas from algebraic geometry back to commutative algebra. Because the result is clearly kind of algebraic. We just described all the maximal ideals. There is no geometry in this result.
So this means that we can identify affine space with spec m?
Yes, exactly. So this spec m of the polynomial ring is just the affine space. And that's one of the possible definitions of the affine space. In algebraic geometry, you define an affine space an as a spec of this polynomial ring over any field, not necessarily algebraically closed, but you take spec, not spec m. So it means that you add all the prime ideals and you consider them as additional points. So that's a proper definition of the affine space in algebraic geometry. Okay. Yeah, maybe let me just write this. Spec m of the polynomial ring is the same thing as the n-dimensional affine space over K, of course, if we assume that K is algebraically closed. Oh, and sometimes also people reformulate Hilbert-Nullstellensatz ansatz as the following identity. So you can, if you take an ideal in the polynomial ring, well, you can consider the vanishing set. Well, say again, so let's assume that K is algebraically closed for simplicity. You can consider vanishing set of this ideal. That's some closed subset in the Tarski topology in the spec M. So then we can consider the Z of this subset. So now this is just all polynomials vanishing on this set.
Algebraic.
All polynomials vanishing on this given set.
So the set is algebraic zeros of these polynomials we take. Like
So V of I is the set of algebraic zeros of I,
yeah,
and the Z is the set of polynomials vanishing on this set
yeah.
as a subset in the affine space. So what's the answer for this?
I
No.
radical.
Yes. So the Hilbert-Nullstellensatz tells us that the answer for this is the radical of I. So that's another way to formulate Hilbert-Nullstellensatz equivalent statement. Well, because we proved that there is a positive M such that, well, this is element in the Z is this element polynomial F that we consider.
Intersection of all maximal, yeah, containing I.
No, what's important, we only prove that there is some power M, right? Such that F to the M belongs to the original ideal.
Yeah.
So this is not about the Hilbert-Nullstellensatz, it's about Nullstellensatz that I just erased. And when I erase this, I have the space to write the same statement.
Okay.
So that's the same thing. It's just a comment. Okay. And now, I think this is the last non-trivial statement in this section and also in this chapter. So, if A is an algebra of finite type, of course over field, so over some K, we consider ideal in this algebra. So then we can compute the radical of this ideal. So remember that we can define this as as an intersection of all prime ideals containing I, but here the answer is that this is intersection of all maximal ideals. So I is contained in M, and M belongs to the spec M of the algebra A, M. So you can compute radicals by taking intersection of all maximal ideals for algebras of finite type. This is not, of course, this is not true for over any commutative ring, but for algebras of finite type, we have this result. Okay, so the proof consists of two parts. So in the first part, I just observed that without loss of generality, I can think that A is just a polynomial ring. I can as well forget about all derivations. Well, that is because you have this surjection. Well, A algebra of finite type just means that A is the quotient of this polynomial algebra by some ideal. So at least there is a surjection like this. So, and then we can use the correspondence theorem. And the correspondence theorem tells us actually that this correspondence between ideals in the A and ideals in the polynomial ring, well, it preserves everything. It preserves radicals, it preserves the inclusion condition, and also preserves the intersections. So by the correspondence theorem, it's enough to prove the statement for the polynomial ring. So since correspondence preserves radicals in the sense that if you take the pre-image of the radical, that would be the same thing as the radical of the pre-image, intersections and inclusions without loss of generality, we can assume that algebra that we consider is just a polynomial ring. Okay. Now we need to prove the statement for the polynomial ring. Well, as usual, we're going to prove two inclusions in two opposite directions. I claim that one inclusion is clear. If you take the radical of any ideal and inclusion in the intersection over all maximal ideals such that I is contained in the maximal ideal, spec M. So this is clear. Do you see why this is clear?
No, because it's we have equality for prime ideal.
Uh-huh.
It's just for maximal, so
Yeah. So inclusion in one direction we get for free, because we already know that radical is the intersection of all prime ideals. Okay, so now we need to go in the other direction. So let me choose a polynomial. So let me call this P. That's a polynomial that sits in the intersection of all the maximal ideals containing M. So again, M is an element in the spec M of A. So I want to show that some power of this polynomial P belongs to the given ideal I. Okay, so of course I is non-trivial ideal, meaning, well, I is a proper ideal, so it's not a unit ideal. So I has an algebraic zero. An algebraic zero. So say A1, AN. Oh, at least we have one algebraic zero. So this is the zero. Okay, and then with this algebraic zero, we can associate the evaluation map. So let's call this algebraic zero just A, and then we have evaluation map at this algebraic zero A. So that's a homomorphism from the polynomial ring to the algebraic closure of K. So under this map, xi is sent to the AI, of course. So then I claim that if I take the kernel of the evaluation map, and then this is a maximal ideal. So this belongs to the spec M of A. Oh. In our case, A is just a polynomial algebra. Right? Do you see why the kernel is a maximal ideal? Yeah, but why this is a field?
Subjective.
How this is subjective? Well, it could happen very well that these components belongs to the K, right? So then the image will be just exactly K.
So K is still a field.
Well, this is still a field, but the map is not surjective.
Yeah, but if the image is all K, then image is a field. So we have like...
Yeah, but the K will be in my example. If all the elements are in K, then the image is K. But potentially, what's going on, you start with the K, of course you have K in the image because you have K here. And then you add some elements.
Oh, yeah.
But when you add all such elements, these are all invertible elements. These are elements in the field. So you adjoin several elements which are already invertible. So what you get is actually a field in the image.
AI is lies in K, yeah?
In the K bar in general. It's algebraic zero, so algebraic zero is a point in the affine space of algebraic closure.
So, and the invertible.
Of course, they're invertible because they're elements in the field.
Yes. Yeah, but why the invertible of AI lies in image?
Well, what would be the image? The image is you take this K, right? And then you to this field K, you adjoin these elements. So this will be K with this round parenthesis about these elements, and that's a subfield.
It's a subfield. There's an invertible element for AI in the polynomial ring of out of AIs. So why in K A1 AN lies AI minus 1?
Finitely generated by algebraic variables over T. Seems like by algebraic closure. So it's finitely generated by algebraic element, hence it's finite extension of.
Yeah.
So it's a field.
Yeah, actually, it's enough for us to know that this is a field. Yeah, so the image is a field, hence, if the image is a field, then the kernel has to be maximal ideal.
Cannot we just say the kernel is x1 minus a1, x2 minus a2, so on and so on? The ideal, the maximal ideal corresponding to the point A.
No, because these are not elements in the K. These are elements in the algebraic closure. So this doesn't really make much sense to say xi minus ai. Okay, so anyway, this is a maximal ideal, and what we also know, well, so since this is a maximal ideal, I claim that we can say that the polynomial we started with is actually in the kernel of the evaluation map, right? Do you see why? Oh, sorry, this is not theta. I call this evaluation maps theta in my notes, but on the whiteboard I decided to call them evaluation maps. So P belongs to the kernel of this thing.
Well, let's see where P goes.
Now P belongs to intersection of all maximal ideals.
Yeah.
So this ideal is one of the elements here, since this is maximal.
Yeah.
So by the definition of P, we have this observation that P is in the kernel.
Why I sits in kernel of evaluation?
I?
Yeah, P belongs to intersection of all maximal ideals that have I. Why I sits in kernel of evaluation?
Because A is its
Wait, yeah, maybe I think something wrong. Wait a second.
No, I think everything's right. I is a subset of kernel of evaluation because
Yeah,
by definition A is an algebraic zero of I, so every element of I vanishes on A.
yeah, yes, that's right. Okay, so we have this inclusion, and this last observation, this works. So this works for any algebraic zero. So we've done this argument by choosing some particular algebraic zero, but this can be done for any algebraic zero. And since this works for any algebraic zero, so we can say that we have inclusion that we want, that P is in fact in the radical of I. No, but by the Hilbert-Nussbaum ansatz. Okay, so we proved the last statement. Now I have the kind of couple of restatements and the definition. So, corollary. So A is an algebra of finite type. We consider prime ideal in this algebra, so P is prime ideal. Well, then for the prime ideal, well, we know that for prime ideal, radical is the same as the ideal itself. So the statement that we've just proved can be, well, for this prime ideal, this implies that this is the intersection of all maximal ideals such that P is contained in M. Right? So clearly this is true. I don't need to prove this. So the radical of P is P, and this is the intersection from the theorem. But this is important since we can give a definition and conclude that this definition is true in this case. So definition, a ring is called a Jacobson ring. If exactly we have this observation, so any prime ideal is the intersection of maximal ideals. So say a ring R. So and this is for any P in this spec. So I can as well formulate this last corollary by saying that any algebra of finite type is a Jacobson ring. So algebras well, saying of finite type, but when I say it's finite type, I mean finite type over a field. So algebras of finite type over a field. So algebras are Jacobson rings. Okay, so and the last thing, which also completely trivial. So if A is an algebra of finite type over a field, well, then there is no difference between the radical of A and the new radical of A, which also immediately follows from this, which is true. So I can as well say that instead of saying algebra of finite type, I can say that Jacobson ring has this property. Okay, and this finishes this chapter about integral extensions and applications of integral extensions to algebras of finite type.
By radical algebra, you mean Jacobson radical of a ring? Like that?
Well, we defined radical, I think, in two ways. Well, we defined the terms as quasi-invertible elements, but the definition that is useful here, this is the intersection of all maximal ideals.
This was Jacobson radical.
Ah, you mean the notation was different?
Yeah, I think
Yeah, so maybe.
J of A.
Okay, J of A. Rad of A is just the same thing, just an alternative notation. So the intersection of all maximal ideals is the same as the intersection of all prime ideals. So next chapter, graded rings and modules. or maybe I can say graded and filtered, but filtered we just mentioned as a tool. So graded rings and modules. So the first section, 8.1, definitions and basic properties. Okay, so I start with the definition of what is a graded ring. So a ring, let's say A, is graded, or if you want to be more precise, we can say that this is, say, n graded, where n is just natural numbers. So if you have the following two properties. So first of all, you can write A as a direct sum of AIs, such that I is, well, this is just some natural number. So this is why this is n graded. Well, of course, in the end there is 0. So this natural numbers with 0. Well, of course, you can slightly change this by using, for example, integers. So then the graded ring has only as components in positive and negative degrees. So this is possible. But in our examples, rings will be graded like this, only in positive degrees. So, and this is decomposition as abelian group. So this is as abelian group. So if you forget about the multiplication, you can decompose this abelian group into potentially infinite direct sum of abelian subgroups. And what about multiplication? For multiplication, we have the following condition. If you take, and these AIs are called sometimes graded components or homogeneous components. So you take the product of an element in the component AI, multiply by something in the component AJ, then you're supposed to get something in the AI plus J. So multiplication respects this decomposition in this precise form, precise way. Okay, as usual, I want to separate my definition into several parts. So this was part 1 of the definition. There will be 2 more parts. So part 2 of the definition, elements of AI are called.
This definition works if I and j are equal.
Sure.
So, yeah.
Well, if this doesn't make much sense, think about the polynomial ring.
Yeah, I thought about that, and I thought about just A0 and A0. I think
I'm going to say something about A0.
Okay.
So elements of the AI are called homogeneous elements. So these are homogeneous elements, and even more precisely, you could say that it's homogeneous of degree I. Or you can as well introduce the function which we can call degree, and degree x is equal to I if and only if x is homogeneous of degree I. So x is an element in the AI. And last part of the definition, if you take any element, so So if x is an A, and you can write this x as the sum of the xi's such that xi is in the AI, then xi's are homogeneous components. Well, these are kind of trivial definitions if you already seen examples of the graded rings. Maybe it doesn't make much sense if you don't know what we're talking about, but I'm going to discuss examples in a minute. So I have, I think I start with several remarks and then I do examples. So remarks are also easy. So what if I take element 1? So in algebra there is identity. If it's homogeneous, and if this is homogeneous, of what degree?
0.
Yeah, 1 is always has to be an element in the A0, just by looking at this property. So say this is remark 1. So remark 2, A0 is a subalgebra, or is a subring. Subring. Again, look at this property. And this is the reason why I use notation A, because I can, well, A is for algebra. This is because I can consider any such ring as an algebra over A0. Automatically, any graded ring is an algebra over zeros component. And last remark, that AI is an A0 module. So all these three remarks follows from this definition, this part of the definition. Okay. Examples. A is equal to A0. So on any ring, you can put a grading such that everything is in degree 0. That's a trivial example, but still we can do this. So example number 2. A is equal to the polynomial ring in one variable. And now I need to discuss how I want to put grading on this thing. And there are many ways to do this. Well, the standard and most useful probably way is to say that, well, of course, A0 is just K as a subring. And then AN is the one-dimensional vector space generated by the x to the n. So clearly, see, this is generated over K. So clearly A is a direct sum of such things. And also this second property is satisfied. Or I can equivalently say that I completely determine my grading if I just say that the degree of x is equal to 1. Right? I can write these formulas, but I can just forget about this and say degree x is 1. This automatically gives me grading here. Okay, the standard grading on this ring. Of course, you can immediately generalize this. So generalize this in two directions. Well, first of all, we can write several variables and also say that the degree of any variable is equal to 1. But you can also do the following. Let's consider A as before. But the degree of x is not necessarily 1. I can as well say that the degree of x is equal, well, some number. So what number I want to use? Say d. This is still a grading. And now, well, that's a good question. For example, d is equal to 2. What's a1?
It's just 0.
0. So if d is greater than 1, then there are a lot of zeros in this decomposition, but still there are several, well, still infinitely many non-zero parts. If you wish, you can even write a general formula. So in this case, we can say that an is the following thing. So this is one-dimensional space generated by the x to the m. So if we can say that m is divisible by d, so say m is no
M is equal to dn.
Is n is equal to dm, and otherwise, if this is not the case, this is just 0. Otherwise, so what we have common in the examples 2 and 3, that x is always homogeneous. Is this always the case for any grading?
What do you mean by that? You can just change spaces.
Yeah. So that's the example 4. So the ring is still the same. Well, A0 as before. In all these examples, A0 is just K, and A0 is still K in this example. But now I just say by definition that AN is something which is spanned over the field K by x minus 1. Yeah. So in this case, x minus 1 is the homogeneous element, but x is not. So, okay, so little exercise, if you can generalize this immediately from one variable to several variables. I'm not going to do this, it's not very interesting. So I continue developing some general theory, so next definition. So,
And for several variables, there will be, like, if you get kxy, there will be a1 is just a vector space of 2 dimensions.
sorry, I don't get it. What's the vector space?
There we an is one-dimensional vector space, yeah.
Uh-huh.
And in two variables, there an will be one-dimensional or two-dimensional vector space.
No, not necessarily. Look, for example, for polynomials, even in two variables. Well, homogeneous components are exactly homogeneous polynomials.
Also,
So there's a general.
x squared, y squared, and xy. So there will be at least 3 dimensions. Oh, okay.
So this is three-dimensional. So this is in degree 1, this is generated by x and y. In degree 2, it will be generated by the 3 elements,
Yeah.
etc. So I think for 2 variables, this is n plus 1. But if you have k variables, well, there is some general formula with the binomial coefficient.
Yeah.
Now, in general, the problem of computing dimension of each individual component for a graded ring is not a trivial problem. It's an interesting problem. For example, well, let's develop the theory, and we can return to this. So a map f a to b of graded rings of degree d. So when I'm talking about the map of a graded rings, so first of all, this is a map of rings. It maps sums to sums and products to products. But what about the degree? So this is of degree d, and this means exactly if you apply f to the homogeneous component ai, well, you're supposed to get something, again, homogeneous, but in the homogeneous component I plus d. So it shifts the degree exactly by d. Okay, so can you give me an example of a graded ring map? Say,
K of x to the k of x.
by what's the map?
Just trivial, it will be a degree of 0.
Okay, so trivial, we mean 0 map.
No, just trivial. K.
Identity.
Yeah.
No, identity has degree 0, of course. Okay, how about the map of degree 3?
But if I is equal to 0. Yeah, yeah. So A0 contains in B3.
Yes, so there,
That's strange.
I think that's okay.
Yeah.
There are no problem. Well,
Isn't 1 should be going to 1?
mm,
Shouldn't it be I times
no, I don't think so. Yeah, now I see that there's a problem with 1, yes. Maybe I need to say that this is for I positive. For all positive, I have this property. And for so now I'm a little bit confused.
Yeah.
No, definitely, yeah, definitely want that one is goes to 1. But I also want to have this property for all other elements.
So it's like A0 should be going to B0, but others should be sitting somewhere.
Well, that's exactly the problem. I'm not sure at the moment what I want to do with A0, all the elements which are not equal to 1. Do I want to send them to B0 or do I want to send them to the BD? Okay. Maybe there's something I need to think about, and we return to this in the beginning of the next lecture. So what to do with other elements of degree 0. Okay.
So A0 also seated in A0, yes?
Mm-hmm.
And 0 should be going to B0.
Well, that depends how you think about this. There is 0 element in any degree. So as an element in the abelian group. Okay, so definition, I fix a graded ring. And now I want to define what's a graded module. So a module M is called, so an A module M is called graded if, as before, we have two properties. Well, first of all, I can present this M as an infinite direct sum of the homogeneous components. But now notice that I want to take summation over integers. Even if the ring is positively graded, I don't assume this for modules. Even for positively graded rings, it makes sense to consider such more general modules. So the theory of only positively graded modules is well, not so satisfactory. So this is as before. And how about the multiplication? Well, the property is quite analogous. You take AI, take a product with mj, and this is supposed to be in the mi plus j. So multiplication on a homogeneous element of degree I supposed to shift the degree in the module by exactly by I. Okay. So as before, say this is part 1 of the definition. Part 2 of the definition is this elements of the Mi are called homogeneous of degree I. So you can do also this thing with the homogeneous components. I think this is completely trivial, so I'm not going to rewrite this. So 3, let me say as before. You can consider non-homogeneous elements and decompose them as homogeneous components. 4, this is something new that we haven't seen for the rings. Well, because I have this summation over z, not over n, I can define the shift of grading. So m shifted by I. That's a new module. And as a direct sum, this is again summation over integers. Well, I already use I, so I need to use another index n. But the homogeneous component is shifted by I. Mm-hmm.
Yeah, and what will be shifted ring in consider of A0? Like we'll take A0 and shift it to the something like A2.
No, that's a good question, but let me kind of ask you, it's in a different form. So take a graded ring, for example, this one.
Yeah.
So what's the free module generated kind of by the one element, so free module of rank 1, by element of degree 0? No, how this is? Yeah, the answer is exactly this ring A. Now take a free module of rank 1 generated by the element of degree 1.
Oh, will be
Not the whole ring.
everything starting from A1?
Yeah.
No, it will be exactly R shifted by 1. Well, not R, A. So you can consider things like this. So these are all free modules. They all have rank 1, but the generator sits in different degrees. So that's the difference. For example, you have
Can you say how it will so for kx it will be just like A1. Yeah, we shifted it by 1. So 1 goes to like to the x or what?
Yes.
no. I think it doesn't make much sense. So if
So 1
well, this means that you generate this, say by some element. Let's call this E, right, over A. But now you want to say that the degree of this element E is equal to I.
So like A always generated by 1, and now we just say that 1 is degree of I. Yeah.
No, we're not saying this about the ring itself. The ring is kind of fixed.
Yeah.
The degrees are fixed. But when we construct,
No,
say,
I mean A shifted. Is
Yeah.
the-
when we construct a module, well, we have a freedom to choose the generators and relations between these generators. So here there are no relations. We're just choosing generators. But since this is graded, I also have, I want free of rank 1, so this kind of give me, so no relations and only one generator, but I still have the freedom to choose the degree of this generator. And if I can choose different degrees, then I get different modules. So as a graded modules, they are not isomorphic. So over a graded ring, there are infinitely many free modules of rank 1. Namely, this is the set.
Why are they not isomorphic?
No, not isomorphic. Say if you want your isomorphism to be a map of degree 0. If you allow maps of any degree, then everything is fine. So now let's go to the fifth part of the definition. So a map F I think here what I really want to consider only maps of degree 0, to be honest. Map of the graded rings. So let's say f a to b is a so map of graded rings of degree 0, and since they always of degree 0, if I have this, I think this would be the right definition. So for rings that consider only maps of degree 0. Otherwise, we can't kind of have a consistent definition with the property that 1 is mapped to the 1.
Yeah.
So now I think this makes sense, with kind of smaller set of the maps, but for rings that's all we have. But for modules we can consider maps of all possible degrees. So this is a map F of graded modules of degree d, if of course we have f of the mn sits inside of the n plus d.
Can we say
So
such a map? Then we also have map from like m shifted to
exactly. So equivalently, any map of degree d is the same as map of degree 0, but now you consider your map from the m to the nd. So when you have the shift of grading, you can talk only about maps of degree 0, and then reconstruct maps of all possible degrees by using this shift. And finally, part 6, which is essentially more or less notation. So home over some graded ring A. Or sometimes to indicate that the ring is graded, people write something like a bullet, that this is A with the bullet, meaning that there is a grading on A. So home of degree D, and the same for modules actually. So you can also put a bullet everywhere to indicate that this is a graded object.
Can we say that this is the same as a map from m shifted to the minus d?
Yes, that is also correct, because this shift operation is kind of automorphism. So this is as well m shifted by the minus d mapped to the n. Oh, but yeah, so let me finish this notation and I finish the lecture. So home dA between two graded modules m and n. So this is the set of all maps of degree d. So then what we just observed we can rewrite in the following way. So if I have home d between m and n, this is the same thing as the home 0 between m and n shifted by d, and also the same thing as the home 0 m shifted by the minus d and then n. And finally, there's also sometimes useful notation home with the bullet between m and n. So this is by definition the direct sum over I, which is an integer, home I m n. So in a sense what we've done, well, we know that in the commutative algebra the home set is just again an R module over any ring, right? So if I just consider this the standard home between two modules, that won't be a graded object in general. Here we start with two graded objects, two graded modules, and construct it at the end again a graded module. So this home with the bullet is again a graded A module. So I want to finish with an exercise. So in general, of course, it is true that home with the bullet between M and N sits inside the home. So here on the right, I just forget that there is a grading. There's just a home between two modules. Clearly, any such module which is or sum of the homogeneous components that maps sums to sums and respects the multiplication of the ring, so there is an inclusion like this. So can you find an example where this inclusion is proper? So find an example such that inclusion is proper. Okay, so that's the end of today's lecture.